This is the Empower Podcast, released March 27th, 2022. Episode 583, sponsored by Mouser Electronics. The Smart Grid with Paul Zawada.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
And I'm Paul Zawada with Syntonus LLC.
Hello, Paul.
Thanks, Paul, for joining us. Hey.
I am honored to be here. I've been a longtime fan of you guys, so I'm happy to join you and share a little bit on power.
How much have you been pulling your hair out over the years as we attempt to discuss power stuff?
There might have been a little bit of yelling back to the podcast, but not too much.
I think it's also a measure of how little we know and how interested we are in the space. So this all came up. We were talking about Smart Grid a couple episodes ago, and Paul wrote in and said, "Hey, actually, I can tell you about this stuff." And Dave and I are both like, "Well, we got to both be there." I mean,
of course, when was the last time we did a three-way with the?
I think 2016, maybe. I don't know. It's I guess usually Kaisermas is the main
right.
one.
That's it. Yeah, we do that once a year, but. Yeah. Anyway, so you're going to tell us all about power because us regular EE dummies, E is not electrical, it's electronics. So basically we know that there's this thing on the wall where power comes out of, and there's like there's
it looks different where Dave is than where I am.
Yeah,
too.
it does look a little different over there.
Like a scream mask, our one.
Yeah, right.
And then there's like these transmission-y line things, and then there's like spinny things at the end of those. So that's probably, and there's big transformer-y things.
Yeah,
so that's probably the limited of our.
Yeah.
Is that so? To give you a little information on my background, I am not a hardcore power engineer. So my background originally was in telecommunications, but I became what some people call an operational technology engineer. And operational technology is kind of that computing and communication stuff that gets wired to the physical devices. And it could be in the power industry or transportation or pipelines or what have you. But it's that combination of that, maybe that hardcore, those big alien things that you guys were talking about last time in the substation yard, and the merging of that stuff with the electronics that have things like embedded systems and network connections and that kind of thing. So that's kind of my area.
Measurement.
And so
that makes sense.
In my work, what I do is I spend a lot of time explaining technology stuff to power people and power stuff to technology people. So I kind of felt that's one of the reasons I wrote in, is because I really felt that that's kind of my niche is sort of straddling that border. So
we need you. So
how do those conversations normally go? Like, especially I'm curious because some of it, well, you're talking to dummies like us, we're going to be like, okay, megawatts, sure, whatever. And I'm in the other direction too. Like, is it kind of like a hard sell, or are they excited about implementing new technology? Or is it more like, well, we've always done things this way? Like, what is the appetite for new technology in the power?
Yeah, it's interesting you mentioned that, because I wouldn't say the appetite for new technology is not that great. We do adopt new technologies all the time in the utility industry, but once they latch onto something, trying to move that to something more current. So the way we do things, say in the SCADA world, for example, it's the same types of things we were doing 30 years ago. And so it's trying to move, say, the power person that has been doing that thing the same way for 30 years is kind of difficult. But
just waiting for him to retire or
right.
You're right.
Otherwise.
The other difficulty tends to be going in the other direction. You have IT people who know IT very well, but they don't necessarily understand the ramifications of, say, what happens when the network goes away. So in trying to explain, how a blackout happens, for example,
right.
And why that network service or that computing service that they're providing, why it is so critical to making sure the lights stay on.
a lot of people are going to ask, well, how does a blackout happen? Because a lot of people, like, that's something that actually affects all of us, and we don't necessarily understand it. Like, yeah, the grid gets overloaded, or there's, power shuffling around from state to state, and there's, load balancing and all that sort of jazz. Should we start there, or is there a particular order you want to take us through in terms of like learning this? Should we start with generation and then go through transmission, or how do you want to do it?
I mean, that's a good place to start. Is, you have in the utility industry, electric utility industry, you have generation, transmission, and distribution. And generation is those bulk power plants, right, that are providing hundreds or some cases thousands of megawatts of power into the system. Transmission is the long lines that get it from where those bulk power system to where it's used. And I think they found out a long time ago, 100 some years ago, that it's easier to transport coal by wire, as they called it at the time, as opposed to, they could build power plants close to coal mines or close to large bodies of water. Like in the case of like nuclear, you need cooling water and that kind of thing. So, and sometimes you don't necessarily want to put a nuclear plant in the middle of a large city either. So they have these transmission lines to bring the power from where it's more convenient to generate it to where it's actually needed.
Is there any limit on the length of those these days? Because we've got a 1,200 kilometer line from Australia to Singapore, for example. Are we getting better at everyone says, oh, Australia has so much renewable energy. Why don't you just put one big solar farm in the middle of Australia and then farm it out to the cities on the edges of Australia? And I'm thinking, well, that's a bit lossy.
Well, you have limits in two ways, right? You can have distance, which the way you deal with that in terms of loss is you raise the voltage. So higher the voltage, the less current you send through the wire, the less, I squared R losses, power, consumed by the wire itself, resistance of the wire itself. And so today, most of that transmission for the really long distances is in the 500 to 1,000 kilovolt range. That's referred to as extra high voltage, as opposed to the high voltage, which is considered like 100 kilovolts to 500 kilovolts.
Only 100 kilovolts. Yeah. Oh, yay.
So, and mostly the one megavolt system, the 1,000 kilovolt system, those are mostly in China and Russia, I believe. We don't have any of those in the U.S.
Right.
In the U.S.,
okay.
In the U.S., it tops out at 765 kilovolts. And then, but if you look at China, China is a much bigger country in terms of, especially where they're bringing power, they're transporting power for further distances than typically we do in the U.S. And as you might know,
they have a newer grid as well, right? I mean, that's kind of like they've. Oh yeah, I'm sure some of their tooling is a little bit newer, so they could maybe push that a little bit more.
Yes, they have been spending a lot of money, and they've built up quite a grid, and they're running into some of the scaling limits that we have not run into yet. Be interesting what they learn in terms of building these large ultra high voltage networks and operating them. But then, of course, the other limit is how much can you carry on one line? You only can make the conductor so big. So if you put all of your generations, let's say in the middle of Australia, you would have to run a lot of transmission lines. And I'm not sure if you want to concentrate all of those in one place either, right? Because I'm not sure what you have in terms of storms or whatever, but you want to diversify where your generation is as well. So
I believe they have spider storms down there, sharknadoes, that sort of thing. Everything that messes weather with terrible animals is Australia.
Right.
Drop bears.
So then once you get to the city or the neighborhood, you have a distribution substation that steps down the voltage. So you may have gone a long distance, say 500 kilovolts, stepped it down to say 138 kilovolts for say a network around a city. And then those individual 138 kilovolt stations may drop it down to a distribution voltage of say 13 kilovolts.
Mm-hmm. And for those who want to identify these as they're driving around, you can just tell by the number of spaces, can't you? Like the number of ceramic spaces. So can you give us like a ballpark number?
Yeah, we call it counting the bells.
And counting the bells, okay.
Yeah, because a lot of times the insulators look like bells, especially the suspension insulators.
Yep.
So I think the rule of thumb is like 15 kV per bell, if I remember correctly.
That's what I thought it is. I thought it was 10 or 15, something like that.
So if you see, and generally the towers for EHV are much bigger because you want to get those conductors higher off the ground,
right?
And reduce the electric fields, because if you stand under a 500 or a 765 kV line, if the weather's right, you'll get a static shock from touching a car or a truck or something underneath it. It's so.
Oh wow!
So they have to limit the E field as well.
How much power is lost in that versus I squared R losses? Because we're only talking about 50 hertz, right?
Or 60.
60 in the US.
Oh, well, 60. Yeah. weird yanks. Okay. Yep.
Off the top of my head, I don't know. I couldn't tell you how many, say, megawatts is lost on a 500 kV line, but it's pretty low. I mean, you're not losing enough to negate, say, a power plant or even a fraction of one. It's pretty low.
Mm-hmm.
So, but again, as you get closer, you drop the voltage down. So when you get to the distribution lines, typically a lot of times you'll see like the mushroom size insulator, and those are pretty small. And although you can tell the difference, or at least if you look at them enough, you can tell the difference between, say, a 13 kV line and a 34 kV line, because the insulator is big enough you can kind of visually tell it's a bigger insulator.
Right. So it's actually physically wider, so that it has a longer surface path to go over.
Right. And a lot of times, when we talked about the alien shapes, a lot of that is about trying to provide more surface area. So if the insulator gets contaminated, you're not going to have flashover. And so sometimes you get they have weird shapes, or if you look underneath the insulator, you'll see that there's what they call a petticoat, where
they're little ridges, little
Yep. So that way it, one, the water drips off before it, the whole surface gets wet, but two, it reduces, or at least it increases the amount of area that has to become contaminated. But even in some areas, like coastal areas where you have salt spray, sometimes they do have to shut things off and just hose it down with distilled water just to get all the salt and contamination off the equipment.
That's something I never thought about. Yeah, when you get close to the ocean, saltwater spray gets into everything.
Yeah. So in this chain from generation all the way to home delivery, that sort of thing, we referred to this video about the Ohio Eastern Seaboard shut off, and you and I were talking about that a little bit before we recorded, Paul. But it shows some of the like breakers and where how things failed and stuff like that. But when you think about the control of quote unquote the grid, right? It's this big singular thing as is often discussed. Where do those control points happen that you think about?
So, well, first of all, I think the thing to remember, and I think it's true in Australia, but in the US, there's multiple. Not only are there multiple grids, but there's multiple entities that control different parts of those grids. So a lot of the control is happening at those control centers, whether sometimes they're nonprofit control entities, like a company called, or an entity called PJM in the eastern US. Sometimes they're still controlled by utilities. A lot of times those are called balancing authorities, because they ensure that the balance of generation is matching the load that's taking place. So they control at sort of at a high level, and then the fine grained sort of minute by minute control of the power being delivered, or generated, I should say, is actually done in a control system for whatever type of generator it is, whether it's a steam turbine a wind turbine or a solar inverter, there is a bit of a feedback loop in there that sort of, so that generator tracks frequency of the grid. So I was explaining earlier that to Chris that the frequency is what determines if you have enough generation or not. And Dave, one of the things I was yelling back at you a couple weeks ago.
Yeah,
you said one, something Paul, about. Come on, you can be honest. It's fine. Just one.
You mentioned how there was a lot of solar coming on the grid in Australia, and it was driving the voltage up.
Right.
No, it's driving the frequency up.
Oh, the frequency up.
Yeah.
Wow. Okay, I didn't see that coming.
What is the mechanism for that too? Is that because of the things that's on Dave's garage that pushes it back onto the grid?
I know. Can I have a guess?
Oh.
Can I have a guess? Because I was going to say if you're generating more power, you have to spin it maybe a little bit faster, and therefore the frequency is going to go up a little bit more. But that's opposite.
So think about the analogy that I like is think about you're riding a bike, okay, and you're going down the road and everything, and all of a sudden you hit a hill and you're going to start. And so in other words, and that's like adding more load to the system. What happens to your pedaling? You slow down, right? Because all of a sudden and so if it's not too steep of a hill, you can just pedal a little harder and you can sort of maintain that same rate. If it's really steep, you may start slowing and slowing and slowing. Well, and that's when you're in trouble, right? So it's the same thing with the grid. The individual generators, they can kind of track the frequency, and if more load comes on the system, like if it's a steam turbine, there's probably a little more steam. They can open the steam valve a little bit and they get more steam, and it compensates for that extra load that came on. At some point though, you can't, right? And so if all the generators, if one generator drops off somewhere and all of a sudden all the other generators around it have to pick it up, you're going to see a dip in frequency, and hopefully there's some spinning reserve somewhere that the grid operator can call upon to jump in and help the guys that are still left. And that's what happened with the Tesla battery in Australia. I think you guys talked about that a while ago, right?
Yes. And are we talking about the one that caught on fire?
No, I don't know if it wasn't the one that caught on fire. There was a large Tesla battery.
Yes. The Hornsdale Power Reserve, it's called.
Right. And there was a massive power plant that dropped off the grid. And the Tesla battery was able to pick up the difference.
Mm-hmm.
What happens then? Okay, so say we're living in, sometime in the future, and it was or maybe not even in the future. Say you're just living completely off grid and you have a community of like 1,500 houses and you don't have a generator in the system. Then the same thing applies though, right? But it's just an all electric version of that. Because we always talk about it in terms of generators, but like there's switching circuits in these things and transformer drivers.
So that's the challenge as we move to a more solar and renewable grid that does not rely on big spinning hunks of metal, because the grid has what's called inertia, right? And that's that whole concept, right? Where, if a bunch of load comes on right away, or a bunch of load comes on, things won't just stop right away because things keep spinning, but they will start to slow down. And the problem is with a lot of the inverter technologies, they don't have that inertia. So they're actually developing, that's a sort of a research topic, is the concept of what they're calling synthetic inertia.
Oh, interesting.
To deal with that problem and sort, at some point then you're keeping some of your energy on the side, or you're not necessarily producing energy, but you somehow have to store that or keep it aside so that when you do have a disturbance like that, your inverters can compensate for that.
Right.
A disturbance in the electromotive force.
Exactly.
Yeah. Disturbance in you. Oh, that has to be the name of this episode. Come on, the disturbance in the electromotive force.
All right, we'll think about it.
Please.
Yeah.
Okay, but how does the voltage go up if you've got too much solar? Because the voltage definitely goes up when everyone's solar comes online during the day, and then the voltage goes back down. You're saying it's frequency, but there is actually a correlation with voltage going up there, or is that just
based on what, Dave?
A coincidence? I've measured it. And other
Okay.
references I've looked at said, yes, the voltage can get near. In fact, solar inverters trip out because they reach their upper voltage limit, because everyone's surrounding solar has come online during a really hot and sunny day. We've got 30% of the population here have solar on their roofs, and boom, the voltage goes up and these inverters trip out. How does that work? Or is that, because I can't imagine that's not a thing, because everyone says it's a thing, and I've measured it myself. So
everyone says. So, yeah.
So this is where you're stretching the limits of my power engineer abilities, but I would have to venture part of it is reduce losses in the system.
Oh, okay, right, that makes sense. Yep,
because
it's coming from a more local source, which is everyone's surrounding roof.
Correct.
Right? So there's less losses directly. Yeah.
Yeah, although to some degree, well, it could also, the other thing it could be that you don't have a terribly high inductive load in the morning when things are coming up.
Mm-hmm.
Eventually, I would venture to guess, I haven't looked at this myself, but one thing I would tell you to do is take a look like in the afternoon when things are getting really warm and see what the voltage is doing. Because at that point, when everybody's air conditioner is kicking in, and you're introducing a heavy inductive component, that your voltage is going to probably drop because of that. And that's the problem.
Well, no, that's when it actually goes up. Curiously, in peak afternoon sun, that's when at about 6 p.m. or something like 5 or 6 p.m. It starts to peak and then taper off, which is interesting.
5 or 6 p.m. is your peak solar? I would have said
no. Our peak solar would be like, in summer, like 2 or 3 p.m. But then it keeps rising. The voltage keeps rising, and then it sort of tapers off around 7 p.m. I think, something like that.
Huh? Because
I have to. So it's not entirely correlated. It's weird.
Like one of the issues they've had in Hawaii, which also has a very, very high solar penetration, is that they have, let's take a step back. Let's talk. I told Chris this was going to happen. We need to talk about the power triangle.
Okay.
Power triangle.
Yeah.
And so this is the concept of, people know power is voltage times current.
Maybe we shouldn't assume that. Let's let's start from basics.
We'll start, but that's why I mentioned it. We're starting at the basic, and especially in a DC power system. Yeah. Mm-hmm. If you want to know what we call power,
it's about where my knowledge starts and stops. Yeah.
we take the voltage and we multiply times the current.
Mm-hmm.
And so when we look at an AC system, when we say voltage or current, we're usually talking about the RMS, a type of average of the voltage and current. So when we say it's 120 volts or 230 volts, that is peak to peak. The AC waveform is bigger than that. Mm-hmm. So if you're talking about a resistive load, in other words, no inductors or no capacitors, when you can still do that simple calculation. What happens is when you introduce an inductive load like an air conditioner, or you have something on the system that's capacitive, the phase angle between that voltage and current is going to shift, right? Yep. So it's no longer valid to just take an RMS value and multiply one times the other. When you do that in an AC system, you have to take the angle between the two into account. And when you do that, you get something called the apparent power. But the apparent power is not the power that's actually powering the whatever thing. If it's your air conditioner, which is an inductive load. Mm-hmm. It's a combination of the power that's cooling your house, as well as some of the energy that is in the magnetic field of that compressor, of the motor.
Which is lost, which is not doing useful work. Is that correct?
But see, this is why I want to talk about this, is because it's not necessarily lost. It's true that it's not doing.
It has to be generated, correct, right? It's got to be generated. Yes. Somebody's got to pay for that somewhere.
Well, exactly. And when we talk about so that component of the energy going into that magnetic field, if it's inductive load, if it's a capacitive load, it's the energy going into the electric field across the capacitor plates, right?
Yep.
That energy is stored and released constantly. And so, but what's happening is like some folks may have heard of Eli the Iceman. Voltage leads current in an inductive circuit, and current leads voltage, ICE, in a capacitive circuit.
Here we call that civil, CIVIL, and then current in an inductor, voltage leads current.
That's good. I've not heard that one because it actually uses V, because E is kind of like the old school symbol for voltage.
Exactly.
I'll have to remember civil.
V.
That's excellent.
Yep, civil. So yep, that's how I was taught.
So anyway, so you have the component that is dealing with that energy, whether it's capacitive reactance or inductive reactance. That is what we call the reactive power component.
Mm-hmm.
And so if you draw a triangle, that apparent power, which was the voltage times current, is going to be longer than the real power, which is what your device is consuming. And then the reactive power is the short leg. So this is kind of hard to do without drawing it.
Showing. Yeah, you've got to have the visualization.
Yeah, I mean, I feel like the visualization is tough generally, but some of it it's just like, because when you're driving an inductive load, you have startup costs, right? Isn't that kind of it? And then it's like getting stored in that magnetic field, and then you can kind of harvest that later. Isn't that part of it? Like, it's just kind of time. It's timed, like it's like offset in time.
Correct, but so the energy is not lost per se, but your generator has to be able to compensate for, again, if it in 99% of the time your load is going to be inductive. Typically, only it's like weird industrial processes do you see like a capacitive load, but I think they do happen from time to time. But what happens is that reactive power, which was measured in volt ampere, we call them volt ampere reactive VARs. The VARs is what tends to control the voltage. The real power, like I was saying earlier, that determines the frequency. And so when we look at Hawaii, what was happening in Hawaii, you have inverters that are producing only watts. So they're only on that real part of the complex number plane that the real power lies on. They are not capable of providing, or at least if they are, many of them are set to only provide watts and not provide the VARs. So what we were seeing in Hawaii was they have entire neighborhoods where they have lots of watts. So they're exporting watts out of the neighborhood, but they're having to pull VARs from somewhere else.
Interesting.
Right.
And how would you actually import that then? Like is it just a setting somewhere, or is it someone else has to generate more?
There has to be a generator somewhere that's capable of leading its power factor to make up for the lagging power factor of the.
Does this mean somewhere there's like someone selling like a thing that just takes real power, stores it somewhere, and then powers a generator with it again? Is that like a product that's on the market?
It's called a capacitor.
Oh yeah, there we go.
So if you had only real power generators, you couldn't power inductive loads?
Correct.
Is that really?
That seems problematic in Hawaii, really where people want fridges and air conditioners and such.
That's
and so the way to think about that is it's like it's looking at like that air conditioner as a short,
right?
And so because it's basically whatever it's trying to produce, it exceeds the capacity of the generator, and the capacity of the generator, essentially stops functioning.
Wow. So what does my home solar inverter act as? Because it's essentially a generator. What type of generator is it? Or does it vary?
So most likely what you have, and I don't know for sure, but most likely what you have is what's called a grid following inverter.
Yes.
And it essentially functions, it follows the voltage, and essentially it functions as a current source.
Okay. Right.
And again, that's one of the challenges of the renewables, is that we need more devices that have that synthetic inertia. Well, actually, so that's a different concept. But what would have inverters that have what's called dynamic response. And when you hear dynamic response in terms of an inverter, that means it can provide VARs.
Got it.
When called upon.
When needed, or real power if needed.
Right. And sometimes you'll hear of it. I don't know if you've heard the term a 4-quadrant inverter.
Yes.
So if you think about the power plane, which is a complex number plane, there's 4. If you think about 4 quadrants, you have one quadrant where you're supplying VARs and you're supplying watts. You have another quadrant where you are supplying watts and maybe absorbing VARs. And again, that doesn't mean your inverter is actually sucking up power. When we talk about,
because that's what's implied by a 4-quadrant lab power supply, right? You can get a lab power supply. It can like absorb.
Exactly.
It's like a battery. It can like absorb energy back in. Yeah.
It can act like a load. And so like a 4-quadrant power supply for the lab, it can act like a real load or a resistive load, or it can act like it can have capacitive reactance, or it can have inductive. So the 4-quadrant inverter is the same type of thing.
Right.
And so most residential solar are not 4-quadrant inverters.
Because of money?
Well, I think it's probably because they're probably simpler to build. Yeah. Which in turn makes them money.
Yeah. I mean, even on the other side of when you're driving like an inverter like that, they're probably just like slamming IGBTs on and off, and then like with this big DC rail, right? I mean, that's probably how they're. I don't know. I've never looked, actually. I should look. But
but basically, when you get into trying to adjust things like power factor, you are talking about thyristor type circuits.
Yeah. So higher losses too, I'm sure, right?
Yeah.
Not in the generation, but in the control circuitry and probably stuff like that.
But one thing I want to make clear though is like when we talk about the whole concept of having the power triangle, it's to simplify the math, or simplify the process of compensating, say, for the inductive load. So it's easier to say, since everything is operating at 60 hertz or 50 hertz, depending on where you are, it's easier to think in terms of supplying watts or supplying VARs or absorbing VARs than it is to actually always be doing the math to calculate the reactance and phase angles. If you break things down into a real and imaginary component, and one thing you have to be careful of, you don't call it imaginary power to a power person because they may slap you.
Really? Okay.
Because again, it has to be compensated for. But the idea behind the VAR component is being able to adjust the phase difference between the voltage and current.
So what should we say to a power engineer? Let's talk about VARs instead.
You call it VARs or you call it reactive power, but don't call it imaginary power.
Don't call it imaginary.
Right.
Okay.
Noted.
This week we're speaking once again with Paul Galata from Mauser Electronics. We're going to be talking about digital therapeutics and where they fit in with the modern medicine ecosystem.
I think we're familiar with digital health. This pandemic has caused us probably to be like, hey, I can't show up at the doctor's office. Plus, just our desire for convenience has made us want to get our health in a digital telehealth to make doctor visits. We collect information with our Fitbit, but we're talking about something different than that. You know, we can go in and let's say we have a glucose problem. We can digitally monitor that, where I might get a piece of equipment from the doctor or buy it and check myself out and see what my numbers are and do certain actions. But this digital therapeutics is even beyond that. It's kind of really a subset of digital medicine. See, this whole transition that we're making with technology just pervading and invading our lives is giving us lots of things that we kind of didn't have before. You've probably heard the famous expression, physician, heal thyself, and kind of what this digital therapeutics is.
You called out the difference between monitoring, and it seems like the monitoring might be the input, but the therapeutics is the output. Could you give us an example of what an output would be? So like what is a best case example of a therapeutic?
So this is being used for people, let's say with something like sleep is common, things like asthma, could be even with cancer patients, ADHD, and those type of things, where what they're going to be doing is using some type of software application, and again, often without any external hardware, and then doing certain things based on something that's been tested in the software to help them actually treat themselves. So for example, you might have a software program, let's talk about insomnia. These software applications will somehow help us not only monitor, but manage by doing some type of treatment where we go in and look at what we're supposed to do and then do these actions, so to speak, in the comfort of our home, maybe pre-bed or something like that, of step 1, step 2, step 3.
And this is almost by definition, it's non-medicinal, right? There's no chemical component, there's no pill that we're swallowing. It's just like actions that a doctor might give you in addition to some kind of
that is correct. And really, it's not only as a doctor giving it to you, but it's, if you will, the program or whatever the information behind that, which of course is put together by the medical community, but also, software people and that type of thing, so that when I wake up in the morning and maybe report of I had this many incidents, or this is what happened, or my Fitbit tracker, recorded all my sleep, it will then tell me and indicate to me what I should be doing that next day, so that if things are progressing or regressing, I get different actions of what I should be doing moving forward. And it's going, what am I trying to do in terms of behaviors based on the information that now might be stored in the cloud, and how that has been combined with the wisdom of the medical community to provide me with the best actions. How can we make sure that these have good outcomes? All these things have clinical evidence.
Digital therapeutics have the potential to further extend the digital medicine ecosystem, and Mauser Electronics is covering this and other emerging technology topics. To learn more, go to theampower.com/digital health. And now, back to the show.
So the idea behind these inverters has changed over time. So like the reason everything was grid following, like we were saying, was cheaper. But now we're getting into the point where we need more of that reactive power, and being able to ride through disturbances with that synthetic inertia. And so if you look at the standard, there's a standard IEEE standard 1547 that deals with interconnecting inverters, or actually any distributed resource to the grid.
Can that be solved by government legislation saying, okay, the sales of solar inverters must be half of this type and half of this type? Is that possible?
Well, so this is where I'm going. So the 1547 standard originally said, like in any sort of disturbance, drop off right away.
Got it. Okay.
If it's changed, so now it's completely 180 degrees different, where now the requirements for new 1547 inverters is that you have to be able to ride through some of these disturbances, and you have to be able to deal with frequency changes and have the utility, say, send you set points for the frequency, because there's a phenomenon called the 50.2 hertz problem. I don't know if you've heard of this.
No. Do tell.
So in Germany, and was it the 2005, 2007 timeframe, they had a lot of incentives for people to put solar in. So Germany, and you know how far north Germany is, has a lot of solar power. And when these inverters were produced and configured, they were all set to kick off, to disconnect themselves from the grid if the frequency reached 50.2 hertz. So there were some incidents where there was much more solar generation on the grid that was needed, and the frequency kept rising, and it hits 50.2 hertz. Well, guess what happens? Everything dropped off. Well, what happens when everything drops off? You're in, and
oops. Or wait, does it go up or go down then? Sorry, I've
so yeah, the frequency is going to drop, but more importantly, you've lost all your generation. So now you're in a generation deficiency, and you'd get these oscillations, and power flow oscillations in the grid are very bad.
Yeah. What frequency of oscillation we're talking about? Because I'm imagining this slow inertia of the generator slowly ramping up again. So I'm talking like sub-hertz.
Yeah, they're they're at least subsynchronous is the phenomena. So subsynchronous being right at your 50 or 60 hertz. So you're going to have oscillations that are in the order of hertz of power changing
and what is the physical phenomenon that the badness of that happens? Is like stuff start to blow out, or do devices?
So you get into dynamics of the power grid, and you get resonances and and things like that. And again, you're pushing the limits of my power engineering skills, but those are the types of things that they're looking for now in inverters. And I don't know of a government mandate that says you need to have so much dynamic like voltage support in your inverter yet, but I think it's coming. And especially as we have fewer devices with large hunks of spinning metal providing the energy.
Yeah. So this is why I said perfect before, is I think this kind of gets right into the quote unquote smart grid, right? This is what we were talking about.
I was about to mention smart grid. Yeah. Yep.
So now you had said the 1547, they're going to start sending set points and stuff like that. Is that part of, I'm going to stop saying quotes, but is that part of the smart grid? Is part of that?
I don't know what's going on overseas or in Australia, but in California, which of course, as you might imagine, has a very large solar penetration.
Just for the record, Australia is also overseas.
And we have, I think, the world's largest residential uptake of solar. We're like 40% or 50% home solar uptake. It's enormous because we have massive government subsidies here. So everyone jumped on the bandwagon and free solar.
So, but a lot of the regulations. So California has had this process. It's called Rule 21. And if you want to research on that, Rule 21 is what you want to look at. And because as far as I know, they're in the US, at least, they're the ones leading the charge and dealing with how the smart grid will interact with people's inverters. But to a lesser degree, though, I think Dave was talking about a couple weeks ago about the lack of time of use rates.
Yes.
And the fact that storing energy at one time doesn't necessarily, you can't make, I call that energy arbitrage, right? You store it at one time and you sell it when it's more expensive.
Yep.
So things like it's called automated meter infrastructure do enable that type of meter where you can do time of day rates, because they have essentially the way a smart meter works, or what it does is it's recording, it records power just like, or actually it's recording energy, right? It's power over time. Mm-hmm. And it records typically over some interval. A lot of times it's 15-minute intervals. So in a day, it's recording 96 intervals of how much energy was being delivered typically, or in the metering side of the house, they always talk about energy delivered, energy received. So energy that you've produced on your solar panels, that would be energy received by the utility. So the meters will keep track for each interval how much power flowed and in which direction.
And how is this comms going to happen? How is this smart comms going to happen? Is it going to be comms over the transmission line, just like we have for the off-peak hot water systems that we have here, the 1 kilohertz tones, or is it done via the internet? And
there's a whole variety of ways it's been done. So when I was involved in the smart metering 15 or so years ago, a lot of the technology was proprietary, what they called mesh networks, where packets could hop from one meter to another till it reached some kind of a takeout point.
Interesting.
So you might have a cellular connected device on a pole somewhere that's communicating with internet protocol, or in some cases there's a proprietary protocol. A lot of that technology has moved to a variant of 802.15.4 wireless, and it's called WISUN, Wireless Smart Utility Networks. However, there is some power line carrier type systems.
Yeah.
I'm trying to think. COSIM is the standard that's coming to mind. I'm not 100% sure that's the right one, but there are some. I think it's especially popular in Europe because Europe has larger low voltage networks, right? Because the problem is a lot of those signals don't travel through the transformer.
Exactly. Yes.
So if you in the U.S., when you have say 4 houses connected to a transformer, it doesn't. You have to have a device for every 4 houses on each transformer.
That's just nuts.
But if you're in Europe and you have, say, 200, it makes a lot more sense.
Right.
So there's PLC is another option. But I think as you get into 5G, you may start to see some 5G services, utilities taking advantage of 5G services. I think in the LTE world, some utilities have done meter, LTE under the glass.
Yeah. NB-IoT is like a definite target for that.
And some utilities are talking about putting in private LTEs. The problem with private LTE is that it's hard to, the spectrum is hard to get because, the wireless carriers are all, gobbling up the spectrum and paying billions and billions of dollars for licenses. Typically a electric utility can't really compete. And so, but there are some pockets of private, what they're calling private LTE. So you may have AMI meters that have that private LTE under the glass, as we say.
And then you have all the politics of who owns the grid versus the utilities that supply power to it versus the companies that charge individuals. And there's all this mismatch of companies trying to operate on this, like who owns and controls and sets the standard for the whole
I think you're
thing.
talking about like in terms of the wholesale power.
The wholesale power, the metering and the distribution, and
in the U.S. at least, it tends to be divided between what they call the wires business, which is the T&D side of the house, and the generation. So for many years we had these large, at least many parts of the country, in some cases maybe not so much, but we have these large independent power producers who can sell wholesale power into a market, and then the utilities themselves can buy the power to serve their customers, or they can, in deregulated states in the U.S., you have power like marketing entities, right? I think this is what you're talking about.
Yeah.
I actually knew someone down in Florida who was an energy, he still is, I think, but an energy broker. And so he would be calling people up and it sounds, I don't know.
Because isn't that how the whole the reason the California grid goes down all the time is because of this energy brokerage? It's not a technical thing. That
was the Enron phenomena. That
money thing.
I don't think
the Enron thing.
Yep. That kind of market manipulation is going on, at least to that large of a degree. I'm not really familiar with the power markets as much as I am with the technology. But one of the things I was going to mention is this is what ties us back to smart grid and the inverters is that, up until recently, being like the last 10, in terms of 10 years, in terms of whenever the power, the rooftop solar has become a big thing, everything was these big centralized power plants. But now you're seeing all these generators on the distribution system. And one point I wanted to make about transmission versus distribution is traditionally transmission has been sort of a network. It's a web. Power can flow in any direction on any wire. And essentially it's kind of like a big pool. So you got all these generators dumping water into a pool, think about it. And then your distribution stations are taking water out of the pool. They're taking energy out of the pool, right? Mm-hmm. And so the distribution system traditionally has been one way from the transmission system to the customer. So now the distribution system is starting to look a lot like the transmission system. So now we got power flowing in all different sorts of directions, and the system wasn't really engineered for that.
Which part of that is it? Like the stability or the charging?
Well,
The
no,
economics?
just in terms of the stability and making sure you have the VARs where you need them, and you have the generation where you need them. Because before, everything was these big power producers, and to a certain degree, by adjusting which ones were generating, you could kind of control how the system is functioning.
Okay.
Right.
So it's like knobs that you can turn and monitoring on it and stuff like that. Is that
Right? And maybe in a region you might have had 10 or 20 knobs. Well, now if I got a solar panel on everybody's roof, I have hundreds of knobs I got to manage, right? And so I can't, like right now, in terms of trying to control people's inverters with set points, the utility may say, and this is just starting to happen, you need to set your set points for this range, and they may do it once a year or once every couple of years. But now, when you have a solar rooftop solar system on every other rooftop, you might have to do it every hour, right? And so you can't just email somebody or text them their set point. You need to be able to
yeah, please turn it to 22.4.
Yeah, exactly.
By the end of the
so
week.
That's where the smart grid is going to come in and help us manage. And so,
and the set point is then again that's changing. That's where the frequency cuts off.
It's basically,
is that the idea?
It's going to be ranges and on the voltage and the current, in terms of again how many VARs need to be produced, or it's allowed to produce or absorb. And again, in terms of watts, like if you get to 50.1 hertz, back off by so many percent. So it's a gradual. So they don't want everything to just drop off at once, right? You want things to back off and kind of, have the control algorithm.
Yeah, that's a lot of sophistication then for each individual box, and you also have to know, like, is there a standard of what they're sending? So a packet they send down the line to, let's just talk about a neighborhood. Neighborhood has 20 houses and 10 of them have solar, and they're monitoring at the entrance to that neighborhood or something like that, as this very simple example.
So there's a standard for that communication, and it's being done by an entity called SunSpec. And so they are working with the inverter manufacturers as well as utilities, and as well as folks like cybersecurity people, to make sure that people aren't hacking into your, because again, I mean, it's Internet of Things at this point, and it may not be on the internet per se, but it's communicating.
But it's there. Yes.
Yeah. There's info. Right. There's info being passed. So, for sure. Yeah, you could.
But these inverters, they're already, like mine, like as you said, they're a grid sensing thing. So can't you just do away with the communications and just have smarter, like inherently smarter inverters that just watch for the grid? Or it's, I know I've got to back off here because it should be 50 hertz as the target. So, it's getting too high in frequency. So I should individually I should be a responsible inverter and back off a bit.
And that's, I don't know how smart they can make them. I mean, to a certain degree, I think there has to be some coordination because in order to make, say, the power flow balance out and flow in the right direction, because you may not be able to get power from point A to point B if you don't have enough.
Oh, okay. So you've got to have a higher level authority that monitors and sort of tells things what to do, because the single inverter doesn't have knowledge of what's happening out on the wider grid.
Right. Which is exactly the way the bulk power system today with the large generators. Yeah. Each individual generator has a local control system which is following the grid, but then there's an automatic generation control system that reaches out to these things and tells them where to operate.
Right.
Yeah. It's all about like remote sensing versus localized sensing, right?
I was going to say, you might want your rooftop solar panels in one part of the neighborhood to back off and have them in another part of the neighborhood ramp up in order to balance out where the power is flowing. And I think it'd be very difficult for a rooftop solar at the end of one circuit to know what's going on in other parts of the distribution system.
The limit there would be the transformer, right? Basically, what's beyond the transformer, sort of the individual inverter or generator can't really know as much, I guess.
I'm thinking of more of the conductors in the middle. I mean, certainly the individual transformers will govern how much, say, a group of houses connected to that transformer can generate. I don't think we're even close to that yet, at least not in the U.S. Maybe you are in Australia.
All right.
But in terms of being able to balance out and deal with the voltage fluctuations and frequency fluctuations across, so now we've gone down in scale across a neighborhood or maybe across a city, as opposed traditionally with the bulk power system, it may have been done across the size of a state. So
what would happen in that bulk power generation scenario? So like say a whole section of the city just fell offline, like a huge transmission tower fell off or whatever, and they had all this excess power. Do they can turn it down at the generation plant, but there's still like excess power in the system still, right? Like, so where does that go?
Right. Well, so that's where we go. We were starting off, we talked about how does the blackout happen, right? So you're going to have, if you lose a whole city, maybe not a chunk of a city, it's got to have to be pretty substantial, but you're going to have a whole section of the city drop off. Hopefully your generators will respond from their control algorithm, because actually not producing energy is a lot easier than producing more energy than you're capable of producing. But that's where you get into these oscillations. And so you lose a big chunk of the grid. You could have power flow a different way and maybe trip out a circuit because
it's going to flow somewhere, you're saying, and it's all connected. So then it just might flow down the big transmission lines to, I guess in Cleveland example, is down to Toledo or something like that, or south to Columbus.
The way we prevent that is you have your SCADA system, or Dave probably says SCADA, because most people I deal with internationally say SCADA. You have these SCADA systems that you're bringing data in from all different points of the grid, and you're bringing back your megawatts, your megavars, your MVA, your voltage, and that goes into a SCADA system. And most people think if they know anything about SCADA, they think of the guy sitting in the control room looking at a big screen with a map on it, right? So, but
yeah. For those who don't know, SCADA is supervisory control and data acquisition.
Dave has Wikipedia up. There's no way he knew that off.
No,
offhand.
I've known.
No way.
SCADA. Yeah.
Really?
Yes.
All right. If so,
honestly, I
can't verify.
Supervisory
If
control
so, I'm
and data
impressed.
acquisition.
I'm impressed.
I've done a power class. Come on, haven't you?
Oh, okay. All right.
Come on, seriously, really? You didn't do a power class? I learned a couple of things at least. That's one of the things I learned.
So I point out though, SCADA is not limited to the power industry. That term is used in many different industries. Yeah.
Oh, it's used everywhere. Yeah.
They use that at wastewater plants. And,
it just means the ability to control things remotely and monitor them remotely.
Yep. And hack it remotely too. Don't forget that. That's a rising thing too.
What I was saying though is like those guys sitting in the control room, they can't possibly watch all these numbers and understand the implications of what happens. So what we do is all that data goes into another system called a state estimator. And the state estimator is a mathematical model of the physical grid. And you can kind of think of it like a crude analogy is it's kind of like spice for the grid. You have your nodes and branches and you're calculating currents and voltages through them. Well, the state estimator is doing that. And it's figuring out where the phase angles between one bus to another indicates where the power is flowing. And so they kind of figure out in reverse. And they kind of understand how the state of the grid, right? That's exactly what it's called, state estimator, right? So what they do then, one thing that helps with is like it checks the data in the SCADA system, because you may have a piece of equipment in the substation fail, and it's telling you there's 0 megawatts. Well, the state estimator will say, well, that's not 0 megawatts. There's power flowing through there, right? It's kind of like it's doing Kirchhoff's, right? right? The sum of the currents in has to be the sum of the currents out. So at a basic level, that's what it's doing. But of course, it's doing it across the entire grid. So it's got this snapshot of the grid.
Wow.
So then what they do is they can run contingency analysis of it. So they start taking, and there's these predefined contingencies, like what happens if this generator stops functioning, or what happens if this transmission line trips out? And it looks at the resulting change in power flow. And if the resulting change in power flow from that, at this point, it's only a hypothetical thing, right? Because they're essentially running like a simulation. It's called real-time contingency analysis. If it's going to cause some other line to overload by their analysis, the operators have to go and figure out what can they do to prevent that from happening if that contingency happens. So do they open a line somewhere so power won't flow or direction, or do they tell a generator that they need to start producing more power here and back off another generator there?
Or can they dump it into a load? Are there like loads on the grid that they can dump it into?
That's what I was wondering too.
No, there's not. Because this was one of my questions is like, if you've got like a backup generator on the grid, right? If you've got like a gas generator or a coal hydro backup generator, and it's always spinning, right? You've got to leave it spinning. Like, what happens if that's like where does that just not actually produce anything, or does it go into a load and then as soon as you need it on the grid, or switches it from the load into the grid? How does that work?
So like a spinning reserve is what they call it.
A spinning reserve.
So
yes.
it's a generator that is connected to the grid, but is only supplying a small amount of energy. So its control system has been adjusted to not say follow the frequency, and it's kind of sitting there.
How does it back off? Does it back off in speed, or does it back off in frequency, or does it back off in?
It's the energy being put into it. So if it's a steam turbine, they've closed the valve, right?
Okay, or if it's a hydro, they're just letting a small amount of water fall down through it. Right. Okay.
You're limiting, and actually, to be honest, I don't know how you do it with an inverter. Maybe you switch out a string.
Yeah. Okay.
But that generator is not. It only reacts to, say, a large change in frequency. So if it sees the frequency drop by, like, say, 0.2 of a hertz, then it opened, the control system. So its control system is set up to let to react to slowly accept when it sees a big change. So, but the point, the RTCA, the real-time contingency analysis, is basically you try to eliminate those contingencies that are going to cause something to become overloaded or so. The problem is when you get to a contingency of like New York City falling off the grid, that's not something they can plan for, because that's just a huge amount of energy, right? That all of a sudden we have to go somewhere, and that's when things, trip out and go bad, or conversely, like,
is that like what does rolling blackout mean? Because that's the California thing.
Well, a rolling blackout is a controlled thing. So a rolling blackout is what they tried to do in Texas, but the problem is it's really hard to make it rolling when you have to take a big chunk of load off the grid. But rolling blackout is when the operators see. So let's take the Texas example from last winter. So
this is when everything iced up and there were problems with that, right?
Ah, okay.
Yeah.
Right. So they're losing generation and they're watching frequency go down. So they're saying, okay, well, we got to get frequency back up, cut so many 100 megawatts or tens of megawatts. I don't know what granularity they use, but
of consumption.
Right. So because they can't, there's no more generation to add in, right? So when you can't add in more generation, the only thing else you can do is remove load.
Throw someone over the side of the boat. That's what I know from the movies.
So the idea of a rolling blackout is you cut the consumption and then you kind of establish some new equilibrium with the generation you have left. Mm-hmm. And so then you take turns. And so this part of the city, gets their power back on for so much time, and the next part of the city loses, or maybe it's by circuit, right? you try to.
Oh, so that's the rolling piece. That's what I never knew the rolling was like. Why?
Yes, was it some human, pushing? Oh, this one has to go off.
Right.
If that one goes off, we've got to push another button.
But
here,
what happened in
etc.
Texas is that it all happened so fast that they were just cutting, and by the time things kind of stabilized, they had large chunks of the grid that were de-energized. That you can't really effectively roll it at that point.
Yeah. So then how do you turn that all back on? It's got to be gradual, because like then you open up circuits, so you're like ramping your generation back up, and you have to open up circuits to like consume that power then?
Right. And the problem when Texas was there was nothing to ramp back up for a while. So that's why it lasted longer than if you look at the 2003 blackout, things came back relatively quickly because it was was more of a loss of situational awareness, and a few things went wrong and caused those power oscillations, and things just went south from there.
So was Texas also a problem because I remember reading about like they have a more self-contained grid, so like they couldn't import power then from like Oklahoma or other states nearby, whereas you might do that otherwise.
That was a problem, but if you looked at what was going on that day, the areas outside of Texas were having trouble as well. So it's not clear how much.
It's not going to import it from Florida or something like that. Like it's going to have to go a really long distance to get in there, right?
Yeah. Some people say, well, if Texas didn't have their own grid, that would have never happened. I don't think that's necessarily true because they were having trouble in Oklahoma and other areas as well. So it was.
Here's one thing I don't get though, and maybe I'm just, it comes back to like if you got like your lab power supplies, right, or you've got a whole bunch of batteries, for example, right? You can whack all those in parallel, right? So then you've got X amount of power that can be delivered from your source. So let's say you've got a 1 megawatt power generator, right? It's a turbine generator. Why can't you just stick that onto the grid, or 100 of them onto the grid, and they only use the power, like only if the load requests the power does it use it? Like, isn't like just a voltage thing sitting there waiting to be used? I know the answer is no, and you can't just put infinite amount of generators on the grid, right? But I want to understand why, if my question's making sense.
What's going on though when you're talking about your lab power supply, there is a power source behind the power supply that's regulating how much is going through. So
no, but your load determines how much power is taken.
Right.
That's why I'm saying, like, why isn't the generator viewed as just a voltage source, and then the load takes what it takes, and you can have an infinite number of sources in parallel on the grid? But I know that you can't.
I'm going to venture a guess here, Dave. So, because money?
Well, I don't know. That's the thing. I want to know why you can't just put an infinite number of generators on the grid and just leave them there, and then the loads, us humans who are consuming the load, just take as much as we need, and as long as we don't exceed the maximum capacity, no problem.
Well, to a certain degree, that does. I mean, the thing is that you have a certain number of generators, and like I was saying earlier, there's a control system that is governing how much energy is actually getting converted to electrical energy and being put into the system.
Yeah.
The problem,
but you can't put energy into. That's what I'm saying. You can't put energy into the system. The energy you put in has to be determined by what the load wants to take, right? You can't like force energy into the grid.
No.
Can you? That doesn't seem to make sense. You can't force it. It's what the load determines it needs.
So Dave, your idea here though would be, so let's just say, okay, so there's a box sitting somewhere that can generate 1 megawatt.
Yes.
Most of the time, so you'd have 10 of these available, and you're saying when consumption is low, each box is just outputting a nominal, trickle amount of power, and then as everybody's air conditioners come on, then these generators just come up in response.
No, I'm saying that they're always generating. There's always that power available, but it's only if the load determines it. Does it draw it out?
Well, I think your analogy is like if I take 3 AA cells and I put them in parallel, and I put a resistor across those three cells, it's going to draw a certain amount of current. And I can put put double the load or half the resistance, right? If I put two resistors, and more current is going to flow, right? I think that in that case, I think it's governed by the chemical reaction going on in the battery.
Yes. Okay. Yes, it is. That's where the energy comes from. But the power is the instantaneous power is always available because that chemistry is there to be used.
And so if I put a whole string of resistors in parallel, it's going to consume that chemical reaction is going to happen a lot faster and consumed the energy that's stored in that cell, right?
Right.
So I don't think the analogy quite transfers over to.
Yeah, I'm just wondering how, like, why?
So the point is in that cell there is a governing mechanism, right? That is controlling.
Mm-hmm. Yeah, that is the control system is redox or
right.
something.
So in the grid in a steam turbine, that control system is the one running the generator because if it runs too fast, it's going to you can't. It's going to burn up the generator somehow.
Well, that's what I was going to ask. Like, let's say you've got a hydro generator, because I'm sure everyone can picture, like, water being flowing down the pipe and turning the turbine, right? What happens if you've got that? Like, you've got the maximum, you've opened the valve all the way and you've got the maximum amount of water coming down and it's turning the turbine at its maximum rate, but there's no load that wants that power. What happens? Does the voltage just fly off and blow up the generator? Like, do they have to actively control the amount of water flowing to match the load? Is that?
Well, there has to be current flowing too, right? So
not just water current.
Well, there doesn't have to be. What happened? Well, see, that's the thing. That's what I'm talking about. If there's no load, there's no current flowing, but that turbine is spinning at its full rate. So therefore, does that mean the voltage goes off into
the water will flow through the turbine faster?
Yeah. And so I think that eventually in that case scenario, the turbine, there'd be no load on the turbine. So it'd be like freewheeling basically, and all that water flowing through it would basically blow up, right?
It'd be right. And it wouldn't, the energy wouldn't be extracted out. The energy would be lost in the gravity as it falls through. There'd be no energy being pulled out through the turbine blades because they'd just be free.
And you can demonstrate that with a small, like a DC hobby motor. If you take it and spin it, and the leads aren't shorted, it'll keep spinning. But if you short the leads, it won't spin freely at that point.
It's it's tough. Yeah. I've done that. Yep. Right.
Well, actually, I had a question about this too because I was just watching. I just saw like the video of like arc welding steel. I think it was on the Machine Picks channel on Twitter. But it was like, these high power industrial processes. And when there are loads available, I would imagine like aren't there like smelting plants that are often like located near like aluminum smelting and stuff like that are located near power generation as like they can buy excess power?
Yep. Or nowadays it seems to be more like electric steel plants where they melt down, they recycle steel.
Yeah. Yep.
And those types of facilities, power quality is a real issue because they generate all kinds of harmonics and.
Oh, interesting.
And they have to do certain things to filter. I'm not exactly how they may have some large inductor and capacitor banks to deal with some of that, but I think some of it is how they build the furnace and the electrodes to try to limit the harmonics.
But they don't want to operate just when power is super cheap. They want to just do it all the time. It's just they want to get a good rate as they would probably act as a pretty reliable load, even though they have all this weird.
Oh yeah, and they're probably going to get a rate that's cheaper because they're buying in bulk, right? Just like anything, if you buy a lot of it, you get.
Yeah, when I worked at Samsung, I remember they got a really really great deal from the Texas Power, whoever they're buying from, but they needed they had a service contract because if the power goes out, all those wafers get destroyed, and I think the power company had some liability in there, and I remember something about that, but I don't know what. So, but they were a very good consumer.
Yeah, sometimes there's limits on the liability. I mean, sometimes certainly contractually they can try to make the power company insure 99.99999% availability, but there's only so far that the
acts of God,
the power company. Yeah, and in that case, it's probably the energy provider is not the limiting factor as much as the wires provider, right? Because of the acts of God.
Yeah.
Mm-hmm.
If an energy provider loses a plant, they can go to the market and buy the power from somebody else who is still producing, and cover their, they do have to cover, generation that drops off. But in a market environment like Texas, they can call another energy provider or do energy trading to offset their loss. So in that case, they'll have some kind of commitment of a generating facility that can cover the power requirement. The issue is if the wires go, there's nothing you can do to get the power there.
Ah,
right?
I see. And so those are different entities, you're saying, as well.
In Texas, definitely.
Okay.
And in Texas, the wires company, they can have an energy business, but I think most in Texas, most of the wires company are not in the energy providing business. And in Ohio, the energy companies or the utilities do not own any of the generation. What they do is, for what they call the standard offering. Say if I'm a consumer, and I don't want to pick my power provider, the utilities run a reverse auction every so often, and say for the next 6 months, the companies that do provide energy, they bid on that, and it goes to the cheapest provider for whatever commitment.
I used to be very confused I would get these mailers when I was living in Cleveland that says, switch to us, we'll provide your power. And I just remember thinking, like, how do you get to choose? Like, are you a power plant that's just like going to specifically route me power? That doesn't work, And it's
that's all an accounting exercise.
Yeah, right.
So it's all that's why everyone talks about, eco power, your EV's just powered by coal, right? Well, no, it's not, because I actually pay for extra green power to come from wind, to build wind turbines to go onto the grid. So technically we had this argument a couple of months back, Chris, didn't we? A while back, how that you said that I can't possibly, that my EV is not being powered by wind energy, but I'm paying for wind energy. Therefore, somewhere on the grid is wind turbines paid for by me.
Probably partial turbine, let's be honest. You don't buy that much power. you get the very tip of the blade,
Come on.
One of the blades.
Right, yeah, no. Just the tip.
So the idea is that, again, you have this big pool, right? And you just have a bunch of energy going into it. And you have a bunch of energy going out of it. You can't trace, a specific joule of energy, provided by one plant. You can't trace it through it's just the system just operates as a whole together. You have all, and
only one artisanally generated power, by some mustachioed person riding a penny farthing in Brooklyn.
So really, what's happening is there's what's called a settlement process, and so the market operator looks at all the power that came in for a particular interval, who was supposed to provide it, where did it go into the system, and then they look at all the power going out, and where who provided power to which customers, and then they settle the market, is what it's called.
So if we have any listeners that happen to be any accounting students for God knows what reason, don't go work at a power company, because that sounds like a terrible job. I'm sure it's all computers, but
yeah, the settlement folks at the power companies, they tend to have this job that a lot of people don't fully understand. It's kind of like a black magic in some senses.
Couple gigavars here, a couple gigavars there. Now we're talking some real power,
But
no.
In the I caught you're talking some reactive power there, right. Chris.
Reactive, sorry.
But in the end, it really does influence. Like if you're saying you're buying green power, it does influence the market for more. Because if I'm a wind generator, I'm going to get, so much more per megawatt hour that I generate. I'm incented to build more wind turbines, right? And if I'm a coal generator and if I can't bid into that green power market, then I may not be able to sell energy, right?
Yeah.
So and my power plant may have to be shut down.
Huh. So it's like voting with your feet, basically, but on a bill, right? Or your wallet, I guess. Yeah, that's great.
Yep.
Huh.
Yeah.
Well, nice job, Dave.
Yes, I know. I've been doing that for like 20 plus 25 years or something. Like as long as it's been available, we've been buying green power, pay like an extra 5 cents per kilowatt hour or something for that. So I'd like to, and I used to read the audit reports because they used to release these audit reports of, look, we put on X, we built X amount of, turbines this, year or whatever, and they've gone online and et cetera, et cetera. So yeah, it was all above board.
Paul, how does the turbines going on the grid then? So a wind turbine then, that actually is spinny metal. So does that, obviously it's, interspersed for when it's windy, that helps balance out solar?
So my understanding is that a lot of those wind turbines actually generate into DC, into an inverter system.
Oh, interesting.
Because those turbines don't spin synchronously with the grid.
Oh, right, yeah.
No, yeah, that's
if you look at a
of course,
steam generator, it's going to operate at like 3,600 RPM. That's going to be the speed that it rotates, and so that's what you're doing when you're adding or subtracting steam from the turbine blades, is you're maintaining that 3,600 RPM or 1,800 RPM. It's going to be some multiple of 60.
Yeah.
The wind turbines, you can drive down the road, you can see one spinning faster than another one, right?
Well, they have gearboxes on them, I know, but like that still isn't going to be synchronous with the wind is the wind, right? You get what you get.
Yeah, it's not going to be continuously variable though. Yeah. So how do you adjust it by a tenth of a hertz?
Yeah,
I think it's done electronically.
Yeah. Right. Yeah, I think it must be. What about AC versus DC? Tesla versus Edison here. There's more and more DC, like long haul DC. Is there any talk about it happening on like the more local scale, or is it just for long haul grids?
So if you may know or you may recall, the reason we use AC is basically because of transformers. So AC.
Yes, exactly. Transformers
makes it easy to raise and lower the voltage. Because actually, there's as we've been talking about with reactive power and stuff, there's a lot of things about AC that make it really complicated.
But and the transformers are very efficient too. Another thing I learned from my class, Chris, not from Wikipedia, is that transformers are incredibly efficient. And if you think about it, they have to be, because the mental exercise we were given is that, well, okay, let's assume it's only 95% efficient transformer. What's the energy loss in that transformer? And you work out, holy shit, it's a lot. So therefore it'd melt down. So therefore they must be like 99.9% efficient. They're incredibly efficient devices. Am I wrong?
Oh yeah, they're very efficient. I mean, but you still can put your hand on it and you can still feel more. Get more. So they're not. Oh
yeah. There's some loss. It's not perfect, but it's not like 95%. It's like, it's pretty close to. It's much more closer to 100% than it is to 95.
To talk about the DC part, so certainly DC has been on the radar for transmission for some time, and there's going back to the 70s. There's a line that's been in place in California, that the Pacific DC intertie that ties. I don't know if it's Southern California and Northern California, or maybe it goes further north into to Oregon. I don't remember the details of where it's running, but the limiting factor in that, I think, has been the conversion going from AC to DC and then back to AC. The power electronics is coming around, so it's becoming more feasible and more cost effective, I think. So in the U.S., we haven't seen a lot come online yet, but there's a lot of proposed DC lines. There's one, I think they're calling it the Sioux line. It's an underground line that they're talking about building in like the Iowa area.
Oh.
That's because you can put DC underground, whereas AC you can't really, can you? That's why they string them above ground, isn't it? Or is it?
And that's one of the things that makes that pretty radical, that they are talking about putting it underground, because I mean it's an insulation issue at that point, and being able to build insulation that that prevents the flashover.
I've heard they have to pump like fluid into them.
Some of the underground, they call it pipe type cable, and they have that for AC cable. I mean, that's been a technology, it tends to be used in cities, right, where you're trying to get transmission through, say, New York City, or
if you're in the city, but out on the huge 500, 750 kV transmission lines, none of those are underground. Is that correct?
No, there's sometimes they'll take a 345 underground.
Oh, really? Okay, wow.
And again, that might be pipe type cable. I don't know which has the oil dielectric flowing through it. I know they have 138 that's could be solid dielectric. I'm not sure if they're there. Probably are, because that technology's been around long enough.
Yeah, if you're doing the really high transmission through, from city to city or from plant to city, whatever, I assume that just comes back economics, like burying
it's terribly expensive.
Yeah.
And
the towers are also expensive, but like not as much as digging up that much dirt.
I don't know how this proposed DC underground line is proposing to do it, but in general, DC is becoming more feasible because of the different types of thyristor technology that you need to do that conversion. I mean, you just couldn't do it at scale to do hundreds and thousands of megawatts before, and now with some of the new technology, it's more feasible. So going back to China, they have a lot of DC transmission there too. Yeah. And it's typically done with 2 conductors instead of 3. So you have cost savings in only having to run 1 less conductor, right? And then I believe just DC, there's inherently lower losses because now you're not dealing with you're not losing your VARs, because typically VARs don't move as well as through the system as watts,
right?
And so overall, it's the losses in a DC system are much lower.
And that's assuming you're at the super high voltage, though, right? Because you still want to lose. You still want to have that I2R losses lower.
Yeah. The problem then is when you get to the city and you need to drop it down at the distribution station, and you need to drop it down again in your backyard, or if you're like in say a European environment where you have, like I was saying earlier, a couple hundred houses on a low voltage circuit. There has been talk about, I forget what they're called, like silicon transformers, which essentially they use power. It's kind of like, I think it's kind of like a switching power supply for 7.2 kV.
Oh my gosh.
But I haven't heard anything about that lately. That seemed to be kind of a buzz going on in the industry maybe 10, 15 years ago.
Right.
And I'm not sure what happened with that. And the other thing kind of along those lines, Chris, you mentioned about, I think, I'm not sure, maybe it was Dave, but you're talking about batteries in the backyard, having local storage.
Oh, local storage for like
you don't
a single
have
street.
Solar. Actually, that was the conversation starter, I think. But
and that was another technology that was kind of a buzz 10 years ago or so, and it kind of died off, and I think they're looking at more like neighborhood or community scale storage rather than trying to, because think about trying to bury batteries in backyards across an entire city may not be
that was a different
easy to manage
than what I was talking about. Yeah, okay, I see what you mean. So like localized storage just for redistribution as needed, that sort of thing.
But there was talk about putting those, again, I think a lot of those were 4-quadrant inverter battery storage systems, so they could provide watts or VARs, or they could absorb watts or VARs depending on what was needed on the grid. But I think it was, again, going back to trying to control all that technology, I think it was maybe a little bit ahead of its time in terms of managing those systems as well.
Available parts and stuff, and
Well, no, just building the control systems and the communications
really?
You needed to all these systems. Yeah. But I think that technology, maybe not with inverters and storage systems in every backyard, but that overall technology may be coming back around to deal with the with the rooftop solar and
Interesting.
and small wind systems. Because I don't know if you see it a lot in your areas, but you do see small wind systems as well. Like there's a couple of car dealerships around by where I live that they have one little wind turbine.
Wow, really? No, that's not a thing here. And unless you're out on a farm somewhere, you know.
I was gonna say farms. I've seen actually ads towards like targeting farmers specifically that are like.
And when I say little, I'm talking maybe, 500 kilowatts. So or kVA actually.
Okay.
A lot of times,
right, yeah.
a lot of things are rated in kVA, right, or MVA, because at the end of the day, you need to be able to handle the voltage times current going through that device. So you'll see these smaller wind turbines. They're not the little tiny ones for like a single house, but we're seeing more of those in our area where you have just one or two, or in some cases I've seen like a industrial park where you have several, like little factories that each have their own one or two wind turbines, and there's a company that manages those for them, and sort of it's a little self-contained community wind.
Yeah, that's kind of cool
system.
Keep an eye. I mean, like that's the thing where like I wouldn't know. You just notice the spinning maybe, but I wouldn't be like, oh, I wonder if that's for this sort of thing. So.
Now you wanted to talk about exploding transformers. Tell us, it's a pet peeve? You're not a happy camper?
Chris and I talked a little bit at the beginning or before we started recording, but yeah, my pet peeve is when somebody in my neighborhood or I hear it on TV, they'll say, "Boy, did you hear that transformer explode last night?"
What?
And I don't know if you have this phenomena. I would imagine you do, Dave, but you'll hear these bangs especially like during windy.
Well, we don't, because everything's underground. Everything's underground here.
Yeah,
we don't
that's
have
true.
big we'll have transformer boxes, which will sit, big green boxes, but we don't have overhead ones.
And I don't know the structure of your grid. Maybe you do have it all underground, but like in the US where you have underground, you may have a residential development that is all underground, but around the periphery, you still have overhead to get it from, say, the distribution substation.
Oh, yeah, of course. Yep.
So that bang is not a transformer exploding.
And they're usually talking about the trash cans up on the poles. That's what you're talking about.
Yeah, exactly.
Are you talking about an arc over?
People don't seem to realize that when you have a 7.2 kV or a 19.9 kV primary touch ground, it's going to make a loud noise. It's not going to be a tiny little bzz. Yep. It's an explosion, really. Yeah. Or the other thing, it can be the fuses on the overhead equipment. They're rather big. They're not very big. They're not like what you'd have in a house or in a piece of electronic equipment. They're the size of your arm, right? They are designed when the fuse blows, there's a powder inside the tube. It's called an expulsion fuse, and it makes a rush or an explosion of this material to clear the arc. So there's this rush of gas leaving the tube that contains the fuse. That's what quenches the arc, because a lot of times if you have an arc, the arc's going to continue to burn. You need something that's going to quench the arc. And in a fuse, it can be this I think there's boron is in the substance. And it's a violent explosion because it's got to clear that arc out. In circuit breakers, like in a substation, the smaller ones, it can be a vacuum or oil a lot of times. Yep. Or in older times, it was more oil. Nowadays, it's more a dielectric gas like sulfur hexafluoride, SF6.
That's a fun one. That's the one that makes your voice real deep.
Exactly. Yeah. And it's a very dense greenhouse gas. Yeah. So the environmental regulators have pretty tight controls on. You have to monitor if you get a leak, it's got to be fixed right away and that kind of thing. Yeah. But there's always when you have high power equipment like this or operating at high voltages, you have to have something to quench that arc. And that's the job of the dielectric or
doesn't the AC help with this? Because DC arc fires on houses on solar, of course, on the on the DC isolator, they're famous for catching on fire and burning down your house, because once DC arcs over, it forms a continuous plasma arc, and then it just stays like that until there's no more energy to give. Whereas doesn't AC self-extinguish?
Because AC, there's a zero crossing, right? So voltage is going to go through zero at some point, and hopefully it's going to go through long enough for the arc to stop. But that may not necessarily be enough. But you're right. DC is very dangerous that way. And when you go into a substation, in the control house, typically that equipment's powered by large DC batteries, like 120, 130 volt battery. And some older locations, I don't seem to see it in newer ones, but some of them had 250 volt DC plants. And I've not been around that, but I've been told when one of those 250 volt DC systems shorts out, like in a piece of equipment fails or something, you need to be as far away as you can, because it's pretty bad. Lots of energy being discharged.
You're saying volt, but everything's been kilovolts and megavolts lately. So just wanted to double check. It's 250 volts, but it's because there's a
right. So the protection system has to be designed to operate because it's going to interrupt the AC. In the worst case, it's going to completely de-energize a station. So you need to have a battery system that's powering the trip coils in the circuit breaker that's doing that.
Got it. So it's like a 250 volt battery that's going to drive a motor or like a relay or something crazy like that to like separate physically.
Typically, the substation breakers have some kind of stored energy so they can operate really fast. So they charge a spring, or they have compressed air or some. So you're not driving a motor to open the breaker, because you want that. And typically, like we were talking about the zero crossing, typically they are timed to try to open during that zero crossing to increase the chances that arc's going to be quenched. But you still have a coil that's kind of like it has a latch, right? So you have you have a charged spring, and you have some kind of a latch keeping that spring compressed. You have a coil that opens the latch, and that spring discharges really quickly, and it moves the actuator that breaks the circuit.
That's crazy. And so what is the loud part then? So it's the 250 volt shorting to ground when that goes bad, you're saying?
So no, like in your neighborhood, it's the fuse. It's just a fuse. And again, it's when the fuse burns, when the metal inside the fuse melts, there's this substance around it.
Yeah, it's like a bomb or like a fireworks, right? It's basically a small firework.
And it basically clears out that tube that's got the fuse. So in a substation, typically they're not that loud, except what's called an air blast breaker, which uses
an air blast.
Yeah.
So they use compressed air to both operate the mechanism as well as quench the arc. So that rushing air where the electrodes are, basically clears the arc away.
Yeah.
You don't see air blast breakers as much anymore because they take a lot of maintenance. Again, you see mostly SF6 insulated breakers in modern substation designs.
It's just amazing to me, like I feel like this is half of this stuff is like so mechanically focused, like generators are just, you're putting in mechanical work in order to drive these things, and breakers, you're doing all this stuff to clear, you're basically trying to blow away an arc, it's just crazy like how that all works.
Yeah. And this goes back to, you were talking about the other day about, nobody knows everything. There are so many specialties and so many different pieces that somebody has to be an expert on, that nobody can be an expert in all of it.
Yeah.
And, I'll have I'll have friends they'll have a son or a daughter who's like studying mechanical engineering, and I'll suggest the electric utility industry, and they're like, well, they're not into electricity.
Right. But it's, no, there's a heck of a lot of mechanics.
This is actually a thing that Dave says often that I wanted to get your opinion on too. So Dave says it's a good industry to go into. Is that a good statement? I mean, like,
oh yeah, it's a good industry to go into because it's not sexy, right? Nobody gives a toss. Sorry, Paul, but like most engineers study,
right?
Like they don't.
It's not Tesla.
It's just not a sexy industry, right? And they don't, and that leads to less people, and it's a big it's one of it's. In fact, isn't the grid the largest single construction on Earth? I think, like, if you talk about the entire worldwide grid, I mean, it's the biggest thing that we've ever invented physically.
Yeah, you hear it's the most complex machine ever built, and that kind of thing. Yeah. Oh, yeah.
Yeah, it's incredible, yet nobody cares about it. It just, turn on PowerPoint and your light comes on and yet obviously that's going to lead to, it costs a lot of money to run this. So therefore, I think is there a decent amount of money? Like if you're a specialist in, a grid distribution, design or something?
I don't think it's like going to work for a crazy
no, it's not Apple.
Crazy venture capital fueled enterprises.
Right.
But no, you can certainly make a very good living at it. And I certainly feel like I live very comfortably, and I really like how I'm compensated. So it's not a bad industry by any stretch, and it's very dependable.
Mm-hmm.
I mean, people need electricity, and
yeah, I mean, can you work anywhere? Not like at home, obviously, but like, can you work and can you move to any location in the country?
Yeah, I was going
to
say,
pretty much?
Can you?
Oh yeah. I mean, there's always utilities looking for people.
And is it possible to work for yourself, like being an independent contractor, or do they just prefer to work with the biggies and then can you work as a subcontractor for like a power utility or something?
So my day job, I do work for a very large electric utility, but I have also at times I've taken what I call my sabbatical, and I've gone and done consulting. I've consulted in India and the Middle East and on power projects, on specifically in those cases smart grid type deployments or planning exercises.
Yeah. Mm-hmm.
So yeah, and there's a lot of engineering consulting firms. So typically you'll find, I think most utilities have a mix of in-house versus engaging engineering firms to do their work. So like your smallest utilities are probably not going to have the expertise to say design a substation on their own. They may rely on an engineering firm, or in some cases they'll rely on your Siemens or ABB or depending.
ABB. Chris used to work for ABB.
Not the ones doing the substations though. That's
Yeah, and I think that part of ABB has kind of been at least partially spun off to Hitachi.
Yeah, I think that's right. Yeah.
Because you see a lot of references to ABB/Hitachi now, or Hitachi ABB. Yeah. But anyway, there's a whole range of different utilities. They have different mixes, and some of that goes back to how they're funded and how they recover their investment through rate recovery. Sometimes it's more advantageous to rely on outside sources. Sometimes it's more advantageous to rely on inside resources, and sometimes that changes over time too, depending on how your regulator's treating capital work versus operation and maintenance work, O&M. Utilities tend to make their money on capital. By spending money, they get a rate of return on it. At least the wires business.
Yeah.
It varies on the generation side, depending on if the generation is integrated with the wire side of the business. If it's independent, then it tends to be more market based, and they're not guaranteed a rate of return like the wires business.
One last question: how can you stand those scams? There's energy saver scams that are those freaking capacitors in a box scams. I no doubt you've seen them.
Oh yeah, I've seen them.
Come across them, and like
I don't really pay a lot of attention to them. And like I said earlier, I'm not a hardcore power guy, but still, just write it off as a scam.
What if they put an Arduino in front of those capacitors though, or some other kind of technology?
Right. Oh, that's going to make the difference. Yeah, of course.
Smart grid. There we go. Smart grid.
Oh,
there's a relay.
Wait until they catch on to that smart
you
grid.
got to have something flip the relay.
Yep.
There's the smarts.
Nope, it's still a capacitor in a box with a LED on it.
Paul, if people want to hire you to design their smart grid, or have other questions about your consulting services, how can they get in touch with you?
Well, I am at Engineer Z on Twitter. My company or my side business is Syntonus LLC. It's syntonus.com, although I haven't been too active on the consulting side because I'm also working on a Doctor of Technology degree.
Oh, wow.
Oh, okay.
Well, it's technology, and it's almost like on the IT side, but of course my focus is on OT. But again, like I was saying earlier about like, how do you get utilities to modernize their approach to technology and that kind of thing?
Right.
It's almost more akin to say an MBA, although I shudder to say that because I'm at heart I am an engineer.
Yeah, of course.
But it is more about strategies to how to apply technology and how to and things like, you know, how do you get expertise and how do you find people to do that kind of work? And my consulting stuff is not so much these days, you know, with a full-time job and studies. And even when I'm not on sabbatical from my full-time job, I don't do a lot of consulting on the side. So
okay, well, they can just reach out on Twitter then, and just chat about smart grid.
They can reach out on Twitter. I try to tweet something every once in a while and share my knowledge or wit.
Well, we appreciate you doing that here. This has been very enlightening.
We do. Thank you very much. It's
I think Dave, we're going to be referring back to this episode often during arguments, I'm sure.
Yeah. This will be our go-to episode whenever we goof up. Yeah.
Yeah, we're still going to get it wrong.
Which we always, you know, it always gets in there somewhere. You know, it's yeah. So yeah, thanks, Paul. It's been awesome.
Great. I was glad to be here.
Thanks, mate. Appreciate it. Catch you next time.